Welcome to this session with the title, Counting People with Administrative Data Instead of a Traditional Census. The counts of people or households in a nation by basic demographic and geographic characteristics are the foundation of statistics that support a nation's key decisions. These counts are often estimated by national statistical institutes by conducting a traditional population census. While these counts are of high quality, they are very costly, owing to the need for a large workforce to, for example, collect data directly from households. In contrast, administrative data are relatively inexpensive to collect and often contain basic demographic and geographic characteristics. The key problem with counting a population using administrative data is that they not cover all people in a nation, and some administrative records belong to people who no longer reside in the nation. This invited session has speakers from the National Statistical Institutes of Israel, the United Kingdom, and Italy, who will discuss alternative frameworks to address this problem and will present recent results. The discussant will be Professor Li-Chun Zhang from Southampton University, who has published widely on the use of administrative data to estimate count statistics. Dr. Ahmed Hallel, Deputy Director of Demography and Census Department, Israel Central Bureau of Statistics, will talk about Israel's transition from population counts based on a traditional census to counts based completely on administrative data. He will discuss how the COVID-19 crisis could affect this transition. Dr. Greg Payne is a statistical methodologist at the UK Office for National Statistics, and he will talk about estimating population counts through the linkage and integration of administrative sources, which then undergoes a statistical adjustment to correct for known issues. Nicoletta Cibella and Antonella Bernardi, researchers at ISTAT, will talk about moving from a traditional census to an ongoing census based on the integration of administrative and surveys, and also talk about how administrative data has been used to count people at the municipal level.
Hello everyone. The corona crisis make it difficult for us to carry out censuses. Many countries are dealing with the crisis by adopting strategies that reduce direct contact with the population. Data collection at the next census in Israel is planned in 3 modes: internet, telephone, and field visits. In the general rehearsal held in 2020, only the internet and telephone phases were performed, and we were prevented from completing the field work. This led to postponement of the census to 2022. The corona crisis was also an opportunity to use administrative data for decision making. The decision makers requested very up-to-date data for crisis management. The use of population-based population census data conducted in 2008 has become irrelevant. This crisis has taught us an excellent lesson. Decision makers, users, are asking for available and updated data that is fit to their use. Accuracy is very important, but accuracy alone is not enough. Israel is examining the possibility of moving to population counts that based completely on administrative data for more than 20 years after the 1995 census. In this presentation, I intend to present an overview of the evolutionary process from a traditional census to an administrative census. In the process, I will present the problems that exist in the population registry, that make it difficult for us to move to an administrative census and present our plans for improving this data. In the end, I will try to answer the question, are we ready to move to an administrative census? We will begin by presenting the main features and variables of the population registry in Israel. It's established at 1948, some months after the independence of the state. It has a unique ID. The unique ID, the use of unique ID is intensive in the public and private sectors. The variables include ID names, address, birthday, sex, family ties, marital status, religion, nationality, immigration date, country of birth, country of father birth, and border control information, departures and arrival to Israel based in the border control system. So, in Israel, 6 censuses were carried out until yet. The 7th census was postponed from 2021 to 2022, and we are beginning to think about the census that will follow this census. The first census in 1948 was conducted after the establishment of the State of Israel. Its main purpose was to register the residents. This registration is the basis for establishing the population registry after that. The 4 censuses that came after the first census were traditional ones. In these censuses, and especially in 1983 and in 1995, the population register was used to ensure population coverage. The enumerator kept in his hand a list of people registered as living in the apartment and their family ties. After completing the questionnaire with the family, the enumerator compared the list of people in the questionnaire with the list of people in the population registry. If there are gaps, he will question the family about these gaps. If necessary, the enumerator add more people to the questionnaire. After the 1995 census, the last traditional census, we began to think about moving beyond the administrative count of the population. In 2008, the 2008 census was a census that integrates data from the field with administrative data. Every statistical area was divided into small cells, about in average, it's 50 households in each cell, and about 20% of the cells were sampled. For each cell, we received 2 independent lists of people. People found living in the cell after the area scan, and the list of people registered as living in the area. Comparing the list according to the dual system estimators allowed us to correct the data of the population registry and produce a population counts for each statistical area. The 2022 census is also integrated census, but the sample is a sample of people, of persons. Sampling of 7% of the persons when resampling in the same family is avoided. The questionnaire refers to all persons in the households of the sampled person. For each sampled person and the household members and his or her household members, we know the registered address on the census day, and we will know the usual resident address after the interview. This will allow us to count the population at the level of a statistical area. We started planning the next census as an administrative census. The part of the population count we will have made great progress, and we believe we can be ready in the coming years to move to an administrative census, at least in the part of the population counts. By the way, we produce a detailed population count also between the censuses. The last census is always used as a basis for counting the population until the next census. Every year, the counts are updated using a civil registry that includes births, deaths, marital status, international migration, and internal migration. In the population register, if the population register has existed for more than 70 years, then the question arises, why do we not move to the population count according to the population register alone? Two major issues prevent us from moving to an administrative counts. The first one is immigrant stock. Do we have the ability to separate those registered in the registry and living abroad between this group and between the resident living in Israel? Or in other words, the ability to build an immigrant stock. The second is the address of the resident updated in the population registry and in the same as his usual address. We have differences between the registered address and usual address, resident address. Now I will talk about the immigrant stock and the development of the immigrant stock. Towards the 2008 census, we have developed a method that allows the construction of immigrant stock. The method based on the border control registration, using the ratio approach between days in Israel and the days spent abroad. For about 10% of the active people in the population register, their usual resident is abroad. Some of them may died in abroad, but we don't know. But it's not matter the population estimates, it's matter more the immigrant stock. In 2000, we evaluate the immigrant stock using 2008 census data. What we found that overestimates of the immigrant, if you look here, percent of immigrant stock, the overestimates is 3.2%, the underestimates is 7.6%, and the net is 4.4%. What is overestimating the immigrant stock? Of course, it's underestimate of the population. And the underestimate of the population was 0.23% and 0.53% the overestimate of the population, and the net is 0.31% of the population. It's good situation. It's good situation, but we have to improve. Since the 2008 census, we have started improving the immigrant stock, and we moved from a stock preparation approach to a stock that management along with flows, departures, and returns. We improving the criteria who is immigrant, updating the population counts using stock and flows, new immigrants versus return immigrants. New immigrant is a person who are a new immigrant is not in the, he or she is not in the immigrant stock. He or she having appearance of an event of being continuously abroad for at least 90 days. After a year from the start of the event of 90 days, he or she has at least 270 days abroad in total. Is ratio of 9 to 12 months. Return immigrants is in the immigrants stock. If he is not in the immigrant stock, he cannot be a return immigrant. Appearance of an event of being continuously in Israel for at least 90 days. After a year from the start of the event, he or she has at least 270 days in Israel in total. It's not continuously, in total. Only the first 90 days it's continuously, and other the year, and the year is 270 days. So we evaluate the method by signs of life in Israel. For example, we use employment data to evaluate it. The results indicate high accuracy. But during the Corona crisis, there was an opportunity to re-examine the signs of life of immigrants in Israel. We checked the percentage of people who underwent a COVID-19 CBR test, and that's the results. If we look for people here, for people who usual resident is in Israel, 40% of the Israeli usual residents underwent a CBR test. For people who usual resident are abroad, the immigrants, only 3.5% are underwent a CBR test. Is this a model error? Not necessary. Not necessary. We examined these cases and found that many of them were on a short visit to Israel in 2020, and some or many of them returned to live in Israel. We have also returned every year, but especially in the Corona crisis, many people came back to Israel to live in Israel. We started with the data of the end of the population of the end of 2019. It should be emphasized, those returning from abroad for a part of the year, they are required to undergo a CBR test examination upon entering Israel. So I think we are in an amazing situation in the level of the national population counts. We have a good situation in the national population accounts. The second problem, the addresses, is related to the local population counts. What is this? The goal, our goal is population counts in statistical areas. What is a statistical area? Localities that count more than 10,000 inhabitants are divided to statistical areas that includes in average 3,000 inhabitants. Localities that count less than 10,000 inhabitants not divided and considered as one statistical area. We have in Israel more than 3,000 statistical areas that we need to conduct for each one a population estimates. Of course, the problem is the differences between registered address and usual address, as I mentioned it before. About 20% of the population are living in an address that differ from the registered one. 2/3 of them are in the same locality, and the other third is in other locality. So our main solution for correcting resident addresses was to look for additional administrative sources. We now use only the population register address. We have an additional administrative sources that have a different address for the resident. Then select one of the addresses as usual residence. We use until now 4 additional administrative sources: municipal tax payment, what we call Arnona, electricity payment, student registration, and employed registration of the tax of authority. So for 3% of the population, there is at least one additional address than that of the population register. These data are data of the 2017 pilot. We predict the usual resident address, one of the addresses, using machine learning models. I have no time to enlarge the speech of these models, but I talk in general about the results, about the findings of the models. First, we built the model using training data from the 2017 census pilot and implement it to the test data. After then, we implement the model to a labor force survey and social survey. So that's the results. The meaning, the results, we can look first of the column of the potential. What is potential? The meaning of potential in the first column is the percentage of people in the population whose one address is the correct address, the regular address or the usual resident address, for 97%. And there are no different between labor force survey and social survey and the census pilot. For 97% of the population, there is an administrative address, which is the regular address, the usual resident address. Oh, it's amazing. Or in other words, according to the current data sources, for 3%, we will not be able to correct their addresses in administrative. One of the main results of the prediction is the measuring of, for each address, the probability to be the correct address. We can locate each person in all his or her addresses with the probability of correct address. But we choose the strategy of choosing one address, the address with the highest probability. The column here, we use I present the percent of people that we choose for them the highest probability with no conditions. In the other column here, we add one condition. The highest probability must be more than 50%. And there is no difference between the two strategies. But if we can look for this model, we know now that we need to improve the prediction, because our goal is to get the 97% people who has a correct address to correct for them the address. And we lose now about 5% that we predict for them the wrong address, a wrong address and not the correct address. So we, I think we can say that we have to improve the models for something. So as concluding, significant improvement, we are at an advanced stage of completing the evolution from a traditional population count to a count through administrative data. Significant improvement relative to the initial conditions. We have, first of all, we have a significant improvement relative to the initial conditions in 2008. Additional administrative sources that include a different addresses than that of the population registry. We now examine some of them, some of these additional administrative data. Adding additional features to the database that will allow for more accuracy in our models, in the machine learning models. We will use the 2022 census data to evaluate the models and improve them. And we also continue of model improvement after the 2022 census. And I can conclude as a general evaluate, move to an administrative count of population within 2 to 4 years after the 22 census. The transition date is a question of perspective. Also, I present that the transition will take 2 to 4 years, but I am optimistic and think that it is possible to move within 2 years. This depends on the accuracy of the models that will be received after the census and should not rule out the possibility that we will move to an administrative count even if the models are not perfect. Thank you for your attention.
Good morning, good evening, whatever the hour and wherever you happen to be joining us from. I'd like to thank you for taking this time to come listen to our talk. So I'm Daniel Ward. I'm an assistant methodologist at the Office for National Statistics, and today I'll be talking about a fractional counting approach for producing administrative data-based population statistics. So to this end, I'll begin with a brief introduction to our project, followed by setting the scene for a post-census scenario in the UK and how it might be possible to produce low geographical level multivariate population statistics using administrative data and survey data alone. So to achieve this, I'll describe the fractional counting approach and how we use it by modeling target population inclusion and address weights to produce these statistics for different characteristics. I'll then finish off by describing how these fractional counters can be rolled forwards over time as new data and survey data, new admin data and survey data becomes available, and subsequently how we plan to continue with this work. So to give a brief introduction, in a post-census scenario, there are a number of methods that we can consider using to produce population statistics. So in our work, we consider a fractional counting approach. So this utilizes available relevant administrative data supplemented by survey data in an extended population data set format. So the aim is to build a weighted record level data set that could be used to produce multivariate population statistics across a number of key characteristics at lower geographical levels. So speaking generally, we can think of 3 major approaches to the provision of post-census population statistics. So the first that I'll talk about is the demographic balancing equation. So this is used currently to produce the mid-year estimates in the UK, and it involves updating census statistics based on available admin data of births, deaths, and internal migration. The second is a central population register where individuals have a universal personal identification number. And as such, the main issues to resolve are misplacement and overcoverage of individuals, so individuals who should have been removed from this register. The third approach then is to create an adjusted population data set where you construct a statistical population data set based on record linkage and integration of relevant admin registers, which can subsequently yield national population counts similar to census estimates. So as the CPR approach is unlikely to be feasible in the UK in the near future beyond 2021 due to related cultural and political complexities, we're currently looking to utilize an APD approach, which encompasses the DBE approaches, admin data, component estimation, and bring that into an integrated population data set. So I'll briefly describe how we're constructing our initial extended population data set. So this figure shows broadly how we integrate the individual data sets to create our extended population data set. So panel A is showing the collection, cleaning and stacking of our individual data sets in the first 2 steps. And this is then followed by a pairwise linkage scheme to try and construct the extended data set, incorporating information from across the individual data sets, including key characteristics such as age and sex. We can then use this EPD with the various characteristics across the different data sets to produce our multivariate characteristic estimates later on. So panel B then shows effectively how we use the extended population dataset in tandem with the 2011 census to create a baseline truth for target population and correct address. So with the whole EPD being used to model target population weights and those records with corresponding census records being used to model correct address. So unlike countries which use a central population register, as we're building our EPD from individual base data sets, we can't guarantee that there's no undercoverage. We might miss some records here and there due to record level linkage issues, or just missing from the particular sets we're looking at. So whilst this is the case, as the EPD is currently constructed using the sets that we are using, we expect that any undercoverage is acceptably small, so within a few percent, and we would expect this to reduce further as additional data sets are added and linkage methods are improved going forward. So having created our EPD, we can look now at using fractional counting to produce some weights. So where conflicts exist in the admin data, such as, for example, conflicting addresses, counting individuals as integers according to the most probable characteristic, so picking between an address, can result in bias in any derived population statistics. So fractional counting aims to get around this by distributing individuals fractionally across conflicting characteristic values, for example, the sign-of-life addresses that we find for these individuals. So a sign-of-life address predictor, or a fractional counter, more generally, is given by the equation where AK is a vector of available sign-of-life addresses or any alternative characteristic of person K in the population, and ZK contains all the relevant auxiliary data. So this may be record age, frequency of update for a typical record, other information that we can glean from the individual data sets themselves. So our aim using these fractional counters is to produce both target population and address weights using covariate information from the range of available admin data sets. So the ones that we're using are the patient register, the personal demographic system, both coming from the NHS, as well as some educational data sets. So the Higher Educational Statistical Agency's data set, as well as the English and Welsh school census, as well as some the customer information system data set linked to the benefits data sets. So the steps that we've conducted so far are listed here. So we've developed an initial extended population data set from admin data sources using the 2011 data and the 2011 census data. We've also implemented a dual stage modeling pipeline. So we've modeled the likelihoods of an individual being a part of our target population, as well as residing at individual addresses. So these are stage 1, which is estimating the probability of an individual belonging to our target population, so inclusion, and stage 2, which is estimating the probability that addresses recorded on the admin data are correct, so placing individuals at an address once we determined that they're within our population. The next step then is to calculate an initial hypercube for characteristics. So in our case, we've currently looked at weights by age and sex, but this can be extended going forward, and subsequently investigated potential rolling methods for regularly updating these fractional counters as new data becomes available. So quickly going over how we are quantifying or modeling and then quantifying our fractional counting efficacy. So we consider 4 models currently. So these are logistic regression, support vector machines, random forest, and gradient boosted trees. And in order to quantify the fits, we have implemented a number of classification metrics. These are listed below. And so whilst these metrics themselves aren't specifically important, they are useful for determining hyperparameter values for the individual models, as well as being able to exclude models for being extremely poor at fitting at an individual level. So an example here. So just want to start this off by saying, try not to read too much into these metrics, as well as the differences between them. So these metrics tell us more about the classification performance across individuals. So the likelihood of an individual being placed either entirely within or outside of a target population, as well as entirely at the correct or away from the correct address. So these are less useful at telling us the aggregate performance of the models, and are more useful at telling us whether models are poor at classifying individuals at a record level state. And so, yeah, as mentioned, the metrics are less important for individual model selection than they are for reducing hyperparameter space when fitting them. So just broadly from these, you can see that stage 1 performs well, achieves decent metrics across all the individual models. Stage 2 performs slightly less well compared to stage 1, but all the metrics are within acceptable ranges. And in order to see how the models perform at an aggregate level, we need to look at aggregate values. So moving on to the model fitted weights. So these are the stage 1 or the inclusion weights. So this is figure 1. So panel A shows the aggregate predicted inclusion weights broken down by age and sex for each of the models compared to a comparator. So again, I'd just like to say, try not to read too much into these, and try not to think that your eyes aren't working very well if you can't pick between these lines. I've zoomed in panel B there, a subset of the stage 1 weights for individuals in the age range 18 to 35, as these have the greatest difference. So the main takeaway at the moment is that our model performs well at determining whether an individual should be included or excluded from the target population. And they all perform within a couple of % of each other, and all of them capture both qualitatively and quantitatively the expected stage 1 weights for inclusion in the target population. So instead of looking at them compared to the comparator, if we just take the difference between the predicted weights and the comparator itself, we'll find this figure here. So this shows the percentage differences between each of the aggregated weights and the true comparator, and they all fall within an acceptable range, so within plus or minus 3%, with random forest performing least best at this stage, and the rest being quite hard to pick between them. If you had to, SVM would be the second worst performing, but at this point you're splitting hairs because you end up benefiting or getting positive differences in some cases, negated by negatives others. But the main takeaway being that our model performs within an acceptable range for stage 1. And so we can now look at what happens when we consider predicting correct address across our extended population data set. So these figures show the top 4 panels, A, B, C, and D, are showing the comparison between the true comparator weights. So the solid lines, blue being male records and red being female records, and then the dashed lines being the predicted values there. And so across the 4 cases, across the 4 models, they all perform relatively similarly in terms of qualitative performance. The quantitative differences are shown in the bottom 4 panels, so the percent differences between the truth and the predictions. And the main takeaway is that we are seeing what we would expect if we were to predict addresses across the entire extended population data set, taking into consideration any expected overcoverage. So in these areas or in these age ranges in which we'd expect or could expect some overcoverage, so again 18 to 35s, for example, you would expect a greater level of uncertainty, but also a greater number of individuals who may be found on the EPD who may not necessarily be included in the target population. And so for these age ranges, you can kind of see some overcoverage here. And so the aim then is to use the stage 1 weights to filter out or to weight people with regards to whether they belong or should be included in the target population. So to this end, you can combine stage 1 and stage 2 weights. So doing this, you end up scaling down the true address weighted population that you saw in the previous slide. And these top 4 panels are again showing that the predictions are far closer to the truth than previously found, especially for logistic regression, with SVM likely performing the worst by this measure. So the bottom 4 panels again are showing this in greater detail, showing the difference between the predictions and the truth. This is showing that we've managed to reduce the overweighting of stage 2 address modeling from a roughly 50 to 60% to just under 10% in the age ranges with the most uncertainty, so 18 to 25, 35. And at other ages, especially for logistic regression, you end up with differences nearing zero. This is the case also with random forests and gradient boosted trees, except in the case of gradient boosted trees, you end up with a little more noise in the weights, model fitted weights. And so this could be down to hyperparameter issues. But the main takeaway from this is that by combining stage 1 and stage 2, so modeling both for inclusion of the target population and residential address, you can produce aggregate weights that are comparable with what we'd expect from the true census level weighting. So we can see this at a greater level by taking the most best performing models, in this case logistic regression, and comparing the results when just modeling correct address, so stage 2, to the EPD in isolation. So figure A here is showing the predicted population weights when you simply take into consideration placing people at their at conflicting addresses, and you get this 55% overestimation in these previously mentioned age ranges. By combining them, or by effectively filtering and weighting by the target population inclusion weights, you can produce results found in figure B, in subfigure B in panel B. So this is showing weights, again, more comparable to what you'd expect. And in panel C and D, you can see the vast reduction in the percentage differences by combining stage 1 with stage 2 to reduce the overestimation. So we found that the levels of the differences between the predictions and the true population weights comes down due to modeling for target population inclusion, but it can similarly be improved going forward by the inclusion of additional data that covers these particular troublesome age ranges. So additional data that allows us to better capture the individuals in these age ranges 18 to 35. So to quickly mention, going forward, we will be looking at rolling these fractional counters. So this involves updating the predictions on new data as and when it becomes available, whether that's new administrative data sets, updated administrative data sets, or survey data. So a number of approaches could be taken to rolling these fractional counters in these subsequent years. So these range from parametric approaches, where you can use various Bayesian approaches in order to update the model hyperparameters to take into consideration updates to the data set going forward. Alternatively, you can roll an algorithmic setting where you can use machine learning or statistical machine learning in order to roll these data sets with various batching of new data and previously included data in order to capture information from new data sets whilst also maintaining the information that's captured previously. Outside of these, a simple initial approach that we can take is to apply the fitted 2011 model as is to the subsequently updated EPD for later years. So trying this naive rolling approach on a separately derived 2012 EPD using logistic regression and random forests, we found a predicted year-on-year population growth of between 0.013 and 1.8% between the two models using this naive carry-on modeling approach. So this compares to an approximate 0.66% predicted growth according to the mid-year estimates 2011 to 2012. So our predictions right within this range, considering the model hasn't been changed, but there's a slight variation here between the predictions for the random forest and for logistic regression. And so going forward, this is something that we can look into in greater detail, as well as applying the additional more complex approaches for rolling going forward. So mentioning going forward into the future, so extensions to our work include extending the rolling and expanding the hypercube. So this involves investigating how we can roll this forward on a continuous basis over time, as well as extending it to include additional dimensions as we gain access to more administrative data, as well as considering the benefit of making use of wider combined admin data as well as survey data that is available in order to both roll and expand the number of characteristics that we're including. We also are going to look at methods for auditing our estimates. So there are still key questions as to whether a purposely designed coverage survey will be sufficient, and whether there's a specific sample size that'll be required to achieve accuracy going forward. Alternatively, we'll consider whether a large-scale collection, more like a full or partial census, might be needed in order to achieve these levels of accuracy in years going forward then. So I'd like to thank you all for listening, and also thanks to the team working on this. So Jonathan Rees, Almas Muntas, Eva Spaglova, Greg Payne, Matthew Plummer, Alison Whitworth, Michael Hawke, Lee Chung Zhang, and Paul Smith. And I'd like to take any questions going forward. Thank you very much.
Dear all, I'm Nicoletta Cibella. I work in the Population Census Division of the Italian National Institute of Statistics. I present a joint work with Antonella Bernardini, Angela Gheppa, Gianpaolo De Matteis on the use of administrative data in the production of Italian permanent population census estimates. The administrative data are crucial, especially in context of official statistics, to comply with the constraints and timeliness in dissemination, both issues especially relevant for censuses. ISTAT in 2016 adopted a modernization program involving a statistical production based on an integrated system of statistical registers, combining administrative and survey data. According to this framework, we moved to the permanent population and housing census. A crucial component of the census quality is the coverage of the target population. Both under and over coverage must be considered. The transition to a census based on administrative sources of data requires a rethinking of this specific task. The case of a combined population census in Italy based on ISTAT Integrated Statistical Register is now presented. The focus of the work is on the use of administrative data to improve coverage of population census estimation. I will illustrate the implementation in the first wave of the permanent population census, lesson learned, and future scenario. The last traditional census that we conducted in ISTAT was in year 2011. Starting from two pilot surveys in year 2015 and 2017, we moved to a massive use of administrative data for census purposes. In year 2018, we performed the first wave of the census survey for permanent census of population. And we now planning the post-2021 cycle of the permanent census on the basis of administrative data in order to reduce cost and also limit the weaknesses of the actual strategies. The goal of permanent population census are producing the information on demographic and socioeconomic variables at the same level ensured by traditional censuses, to disseminate yearly census statistics related to demographic and socioeconomic topics, to reduce cost and response burden. To this aim, we used register and administrative data and ad hoc census sample survey. Permanent census results are estimation that combines data from registers and survey throughout a proper statistical model. The primary output of the population census are population counts. The estimation process is based on the base population register, BPR data, corrected by means of the sample survey of the two possible sources of error, overcoverage and undercoverage. The overall objective of the permanent census is to produce population counts at the level of municipalities and for some very relevant demographic variables, adjusted for over and under coverage. To each registered record, we apply a correction factor in order to take into consideration over and under coverage. To estimate the quality of BPR, we use the well-known capture-recapture model, and we use at second capture the information coming from the survey. For each individual that belongs to BPR, we apply a weight on the basis of the estimation of overcoverage rate and undercoverage rate in order to produce, finally, the population counts adjusted for the two sources of error. We have two different surveys in order to estimate the over and under coverage of the register and to complete the information that we do not have in the registers. So we have the L survey and the A survey, which is an aerial survey, in which we interview units coming from BPR, or we selected some addresses from a register of addresses in order to estimate the undercoverage of the registers. We also use a thematic database called AIDA, which is the Integrated Archive of Usual Resident Population that has been set up in year 2015 to exploit the administrative sources and to find relevant patterns useful for population counts estimation at micro level, improving the quality of municipal population register and of BPR. Each presence of individuals in administrative source like Labor and Education Archive, Tax Returns Archive, and so on, can be considered as a sign of life. These signs of life are classified according to duration patterns in Italy, time, and reliability of the specific sources. And linking BPR records with AIDA signs of life and survey data improve the estimation of under and over coverage of the register's data. For the wave 2018 and 2019, we estimate the BPR corrector on the basis of 5 principal steps. First of all, we need to construct the variable under and over coverage on the basis of the two sample survey. Then we identify the outliers and we calculate the direct estimates on the not outlier units. Then, in order to overcome the well-known weaknesses of direct estimates, we calculate indirect estimates by means of small area models. And in these 5 steps, we use administrative data coming from AIDA in 2 basic moments. First of all, in order to reduce non-response in surveys using signs of life, and then we use administrative data as covariates in the model. This process presents some strengths. We reduce the survey response, but at the same time, we adopt for the wave 2019 and 2019 a strategy of recoveries not diversified by types of municipalities that are really relevant. And also, we perform the recovery at the individual level and not at the household level. We adopt AIDA in order to correct the possible non-response of survey, especially for some specific subpopulation like foreigners. We consider the signs of life in AIDA. With signs of life, we mean very strong presence on Italian territory. For example, work, study, signs of life in the municipality of residence for more than 8 months in a year, and other similar. And we consider untraceable candidates, non-response unit of the survey with strong signs of life recovered and considered usually resident in Italy. The hypothesis is that someone not counted in the survey with a strong presence in the area can be considered not persons. The raw estimates of overcoverage rate for each municipality separated by citizenship is given by the ratio of the number of sample units in BPR classified as untraceable after applying the AIDA recovery to the total number of sample units. Using AIDA in year 2019, we reduced the raw estimates of the overcoverage rate of about 4 points, because the raw estimates of the overcoverage was 6.1 at the beginning. After applying AIDA, we have that the direct estimates of the overcoverage rate was equal to 2.73. Now, some lessons learned on the estimation counts from the first wave of permanent population census. For sure, ISTAT implemented in year 2018 the first prototypes of register and started up the annual survey specifically designed for census purposes. The response rate for A and L survey was very high, but also the permanent census permits to disseminate results respecting cost constraints and timeliness in dissemination. And thanks to permanent census, we have also that the population counts which produce monthly updates will converge annually on the same population total. But we have some weaknesses of the actual strategies. First of all, even minimal variation response rate and in health survey outcomes can produce very substantial impacts on the total population counts, both in absolute and relative terms. The complexity and the strong dependencies from the survey network is crucial. So we need to use administrative data to reduce cost and the non-ignorable survey response. Also, we produced in the first waves population counts for municipality and separately for Italian foreign citizenship, but we need more detailed data. And we need to produce data that are immediately usable from local authorities with correction factor of 0 and 1, and to delete records with 0 as correction factor from VPR in order to improve the sampling frame. Moreover, census result in Italy has legal value, determining funding levels and availability of services. So we have that the difference between register of population and census population estimates are of a few dozen units that lead to exceeding or being below the threshold of interest to have or to lose funding. So the accuracy is very relevant. So now we are working on improving the overall process. The current investigation areas on which the thematic experts, statistical and IT experts are working are the definition of unit-level small-area models in order to use simultaneously data for 2018 and 2019 in order to reach finest domain levels. We are working on identifying alternative methodological solution for the estimation of the population counts by making it the most efficient use of administrative data in AIDA, and also the information from census survey. And we are trying to apply deterministic approach to produce census count in absence of sample survey, like the year 2020. And the use of supervised and unsupervised model throughout the availability of multiple lists that enumerate the population of interest. Then we need to work to a new design of the aerial survey for the post-2021 cycle to ensure an optimal trade-off between costs and quality of the estimates, under the assumption of investigating a reduced number of sample municipalities. And we are also evaluating the dissemination of coverage results also for some specific other subpopulation like member of cohabitation and so on, or the use of data in AIDA in order to better define the basic population register. The COVID pandemic was a strong pushing factor in the use of data for the production of census counts in absence of survey. That's why we're really working hard on the use of administrative data to calculate the VPR coverage for the year 2020 and also for the post-2021 cycle. We are now working on the use of AIDA for the 2020 census round with some experimentation steps. First of all, we are studying the association between administrative signals and VPR information to define criteria useful for identifying aggregates of under and over coverage in the register. We use, for example, family ties, a relationship among various household members, in order to define additional criteria useful for identifying the usual residence of individuals. And we create and introduce new variables on the basis of these family ties. Then we formalize the criteria by means of a grid on which is possible to define deterministic rules for the classification of individual records on the basis of the variables identified in the previous points. Then we apply the deterministic rule and we classify individuals as candidates for over and under coverage or correctly placed individuals. We correct the VPR and produce the population counts on the basis of the rule we define. Then we analyze the results and compare the results with the disseminated data. Here we have an example of the criteria. On the basis of the AIDA, we have some individuals with a strong work-study science in a province other than the one in which they are resident. So we apply some criteria like the presence of at least one minor who has a signals in the municipality of residence, or the ownership of an exclusive home or lease in the common residence in order to detect who is a possible candidates to overcoverage and who is not. We also work on the continuity of the presence of the work signals at the end of the observation period. So, on the basis of these criteria, we apply on test data in year 2018 the deterministic approach by means of AIDA. And we have an estimation of the total amount of the population. We are considering possible candidates to under and over coverage. The level of the over coverage on 60 million individuals is equal to 1 million individuals, while the under coverage is close to 300,000 individuals. So we have some gray area in which we have no decision to made, and we need to acquire some new sources like the citizens' income, or in order to detect particular subpopulation. Then we can exclude from the eligible population foreigners with expired permits to stay, for example, and we can acquire some other sources. For sure, for this experiment, we noticed that the aggregates that we have from sample survey and administrative data are quite different, because foreigners are more likely to escape the survey, while administrative data capture less of the movement of Italian on Italy. So the current activities regards the evaluation of test results and the refinement of the criteria that we define. The acquisition of new sources, especially for year 2020 in the AIDA DP, the application of the refined rules on the updated DP and DPR, and the evaluation of the results for year 2020. The comparison of the results that we have applying this deterministic approach to the ones obtained by applying 2018-2019 correctors for producing 2020 population counts are also under investigation. So, conclusion. The permanent population census aim at integrating register, admin data, and sample survey to obtain the counts of the usual resident population at specific date. We have a continuous exchange with stakeholders and data users in order to improve the general process and the general strategies. From the first ways, we have some strengths and weakness of the strategy that we developed. And admin data have helped us to cope with some difficulties and shortcomings from the survey. Now, we are working on different scenarios for improving the quality of population counts with budget constraints and for overcoming some weaknesses of the actual strategies. Administrative data are certainly an asset in that regard. The effort that we made are dedicated to face issues of quality and timeliness of admin data, consider the richness of the longitudinal approach, and improve the integration of survey register and admin data to our proper statistical model. At the end, we need to evaluate the quality of the estimated counts by means of the whole integration process. Some references. Thank you.
So in this discussion, I would like to make a summary of the approaches we have seen when it comes to using admin data instead of census. So imagine to start with, you have a statistical population spine, which combines all the relevant admin data into a single statistical register, denoted by R here. And just like a traditional population census or a ideal population register, like what we have in Scandinavian and some other countries, this statistical spine is also aimed at enumerating the target population, U. And this spine could obviously be disaggregated into local areas, as indicated here. If the spine is of good enough quality, such as when it is basically the ideal population register, it can probably be used for direct tabulation of population statistics at quite detailed level. If it is not, so that is the topic that we've been discussing. So the first approach is what I call the two-sample survey register approach. So basically, you introduce a survey which involves two samples to combine with the population spine in order to produce the statistics. So the survey has two samples. The A sample, area or address sample, is used to deal with the undercoverage of the spine, just like there is such a sample you could use to deal with the undercoverage in a population census. The second sample, called the list sample or L sample, is used to deal with the overcoverage of the spine, just like in a census context. You could use a census, a sample drawn from the census to deal with the overcoverage of the census. So this two-sample survey register approach is completely analogous to the two-sample survey census approach. And this is the approach that has been used, for example, in Israel 2008, for the 2008 integrated census, that's called. The area sampling requires a frame which is separate, area address frame, where the population sort of attached to the addresses of the unit in this address frame is unknown. But we could think about one might call one sample approach, where instead of using this initial A frame, we could start by building an enhanced A frame, which is by allocating or attaching or distributing the individuals in the statistical population spine to all the units you have in the address frame. So this is F star, this is denoted by enhanced frame. So you combine the statistical spine with the address frame. And now you can do stratified sampling on this address frame. For example, you might sample differently for the addresses with attached person, without attached persons, or those addresses where you consider the overcoverage error to be greater than other addresses. Whatever, you can do stratified. The basic idea is stratified sampling from this frame. And for those addresses, for every sampled addresses, you will survey for the target population in order to account for the undercoverage of the spine. And at the same time, we try to follow up all the individuals attached to the sampled address in the statistical spine. So these people may be, you may track them up in another address, or you may find them to be out of scope. So this is a way for dealing with overcoverage. So in other words, there's one sample drawn from the area frame, but it's trying to deal with overcoverage at the same time. Now, a person who's misplaced in the statistical spine, under this approach, we have multiple accesses. So a person could be directly sampled at the address this person actually are, or it could be followed from the wrong address, mistaken address, they appear to be in the statistical spine if that was the address that was sampled. So the estimation method can be adjusted to account for this type of multiple accesses. It is also possible, as a variation of this, to say if we don't follow up the overcoverage, So we do not track the individuals that are attached to the sampled addresses, but we only check for the coverage at the sampled addresses. Then you basically have an undercoverage sample. And this can be together with use multiple population register to create a kind of modeling approach using a concept called pseudo-conditional independence. So these are the approaches based on one sample from the area frame. There is another approach which is being implemented in Israel 2021, which you might call register survey sampling approach. So basically you have a population spine with no overall undercoverage, but you have a mislocation problem at the detailed level. So basically the idea was to draw a sample from this spine with the inclusion probability pi, and then for everyone in the sample, you would identify the locality this person belonged to, or 0 if this person is out of scope. This is not the situation in Israel, but in other countries, as long as the spine do not have undercoverage, overcoverage, we still consider theoretically it's a possibility, then you would have that category too. So in this way, you can use an estimator as shown here to estimate basically essentially the proportion of people in a given local area using a standard survey sampling based methods. So that's why this is called register survey sampling approach. Basically, you're surveying the register in order to estimate the population size. The next situation is that in addition to this survey and the spine, you also have something called signs of life data. These signs of life registers are, generally speaking, activity-based and more updated than some normative population registers. And ideally, this sign of life register should only suffer from undercoverage, but no overcoverage, because it's activity-based and updated. For example, utility bills, medical care, etc., etc. In case the sign of life register is not completely, can be sure that it is without overcoverage, you can still use some kind of rule-based trimming to construct a subset where basically, essentially, you think this is the approach, for example, we're seeing being discussed in Italy in 2019. So for the, what's the use of a sign of life register? This first instance is to help the survey, because the list sample drawn from the population spine, in reality, will suffer from inevitably survey non-response. Now the question is, for the non-respondents, you need to know whether it is a survey non-response or it is out of scope. So this distinction and the sign of life register can help in this respect, at least. So in Italy, we've been. It seems like what I understood is that you do some simulations. Do some imputations. So for the non-respondents, you can add to these people who are identified as belong to the population using the sign of life register, the BU, basically. This is like a capture-recapture situation. So the survey respondents is one capture, and the sign of life register is another capture. And this imputation approach is essentially like making the union of the two lists. But of course, you could also consider, I think, a dual system estimator. So basically using these two sources to estimate, for example, the number of in-scope individuals in the sample. Obviously, this basic dual system estimator can be sort of modified to adapt to the situation, but that's the idea. So instead of using only the union of the list, you could try to estimate the ones missing from both. So there are people, so they are under coverage, both due to survey non-response and due to the sign of life under coverage, because the sign of life do not cover everyone. So this is sign of life data. Now, moving one step further is to say that can we So we are moving closer and closer to the fully register-based approach. So given we have sign of life registered, it becomes possible in many situations to do without sample survey at all. So one of the cases has been worked out is in Ireland, where you use a sign of life due system estimation method. So basically, there is a sign of life register based on lots of activities and a holdout sign of life data set, which in Ireland case is a driver's license renews, which that's like every 10 years. So it serves as a second source. So this creates a sign of life register based DSE. There's no sample data. It's all register based estimation. And of course, one can also think about the other possibilities like a trimmed DSE and multiple system estimation based on the same kind of data infrastructure. This assumes, of course, the sign of life register basically has negligible overcoverage. When this is not the case, DiCecco et al. Has done in a number of papers a type of approach called latent class modeling. So basically, for every individual in the union of the target population and the sign of life registers, you will have observed indicators of inclusion in the sign of registers, which is delta 1 to delta k. The one you don't observe is the membership of the target population, and that is defined as a latent class yi equal to 1 or 0 for everyone in this universe. So that creates a setup for the latent class modeling approach. So this, again, you're modeling the register directly, not necessarily any of these sign of life registers is based on survey at all. There is an approach which has been implemented in Estonia since 2012, I think, after the last previous census. It's called a residency index. So the approach starts with an extended population data set in the sense that the undercoverage is negligible. So you do have people which are erroneously in the extended population data set, but the undercoverage error is negligible. And then based on these sign of life indicators, you would construct deterministically a score, mu, which is between 0 and 1, and so that the sum of the mu's over the extended population data set will give you a reasonable population size estimate. That's the residency index approach. Taking this one step further, which is a modeling approach that's being developed in Latvia, is what we call the sign of life logit modeling approach. So the idea starts with a logit model fit to the last census. So you start with the extended population data set, and then here you have the last census data. So you have the observed labels, 1 being in the population, 0 not. So this is just building a predictive model as usual. So once you create that log linear model in the post-census years, so you don't have the labeled observations anymore, people you know the true status, but you do have a vector, a number of sign of life indicators. So you consider these indicators as a measurement variable for the latent membership Z. So that Z is no longer. So this gives you a sign logit model combined for every individual in the extended population data sets, and where Y is observed, but Z is missing. So this parameter estimation can be done by an EM algorithm. So this has a number of sort of natural attractions, because the modeling is not like modeling from scratch, like the latent class modeling, if you want, or the conditional, pseudo-conditional independence type of modeling. It doesn't have this supervised training, if you want, phase. So the logit model is actually identified based on the census data and is considered to be good enough. And you would have continued with it if you had been able to observe enough people with true resident status in the post-census years. But you don't. So you only have the sign of life indicators. So this is why this motivates using a sort of latent construction measurement type of model type of approach. So combining these two, you would have a possibility to update the sign of life logit models over time using concurrent data. And it's flexible depending on what kind of sign of life indicators may be sort of added to the model and or maybe disappearing, so on. So this is more flexible. So this is another approach, which is, again, no sample survey at all. Obviously, you could do coverage survey to check the quality, but on a sort of running basis, it is not necessary. So finally, I think that these different approaches we talked about, for example, the can be all included in a framework, which you might call fraction accounting framework. So, for example, when Israel is checking the locality sort of belonging, that is kind of a placement issue. Whereas in Estonia, Latvia, if you are considered more about the erroneous enumeration part, this is the overcoverage problem. So you start with an extended population data set. And you can also be connected with the census to initiate it. So that's part would be the core part. And then basically you have the probabilities of getting the whether you belong to the population, and given you belong to the population, whether you would be in none of the edges we know you could be. That's called displacement. And if not that, then you must be one of the addresses we know you might be. So depending on you have 1, 2, 3, and so on addresses, we will put a probability on that. That is a mu. So Italy, for example, was talking about some deterministic rules to do that, and that would be amount to say, instead of you using a mu as a probability, you use a classifier. So basically you choose one address as an integer solution. So anyway, so this fractional counting can present a theoretical foundation for a system of statistical data estimation, which can accommodate basically all the relevant information and data you have. And so this is not really an approach per se. This is more a framework. So it is not just a methodological sort of the device, but it is conceptually allows you to basically consider population or the usual residence concept in a more nuanced way. Thank you. I stop here.